Hello, everyone. I'm Augusto, and I'll be introducing Orbits, which is a gaze interaction technique for smartwatches that uses smooth pursuits. This study was done in Lancaster University with collaboration with the Andreas building from the Max Planck Institute for Informatics. To understand why smartwatches came to be, we need to remember what sparked the creation of the early wristwatch. And this happened because early pilots had serious difficulties reading their pocket watches while flying with both hands in the controls. When Louis Cartier heard this story, the French jeweler, he came up with the first prototype of a wristwatch that enabled aviators to time their flights without taking the controls, their hands out of the controls of the plane. 100 years later, and wristwatches are literally computers that you wear on the wrist and provide much more than timekeeping functionality. Devices as big as the original wristwatch can now enable you to text your friends, to read the news, or even take pictures. But while the computational capabilities of the devices grow with each day, accessing and interacting such a vast range of functions through such a small touch display, it's a big challenge for both designers and developers. This is a very well-known problem in HCI and is known as the fat finger problem. And it happens when the user occludes important parts of the screen when he's providing touch input, or when he acquires the wrong target because multiple targets are displayed in close proximity. And several interaction techniques have been developed to deal with these issues, especially for smartphones and tablets. They include spatial gestures on the display, clip-on controls that extend the input capabilities of these devices, or even touch on the back of the device. And while these techniques work well on most smartphones and tablet computers, they do not scale down appropriately to the form factor of a wrist-worn device. Smartwatches simply do not offer enough screen space for spatial gestures, and relying on clip-on controls or touch in the back of the device, it's either impractical or unfeasible. As such, most new interaction techniques for smartwatches tend to decouple the input and output space, moving input to the strap, to the edge, or even above the display. Other examples use the face of the watch as a mechanical interface. You can physically twist, tilt, and pan. But while decoupling the input and output space of these devices successfully enables interaction, all these examples still require some form of manual input. As such, they ignore the key affordance and intent of the original wristwatch, not just information at a glance, but also hands-free operation. As such, to accomplish this, we propose Orbits, which is a novel interaction technique that enables gaze-only input on smartwatches. In its most basic form, Orbits are graphical widgets with a target that moves in a circular trajectory. The user interacts with these widgets by simply following the target with his eyes. So for example, Orbits control for a light switch could look at something like this: an abstract target that orbits a graphical representation of a light bulb. Once the user follows this target for a specific amount of time, it turns on the lights on or off. Furthermore, the same widget can have more than one target, for example, for increasing and decreasing the brightness of the room. So following the target that moves clockwise, for example, could increase the brightness of the room, while following the target that moves counterclockwise could eventually decrease it. So how does Orbits work? Orbits works by correlating the position of all the targets on screen with the user's gaze. Because we do a correlation between two trajectories, we deal with normalized data, which means that the user's gaze does not need to have a one-to-one mapping to the target's trajectory. As such, gaze data can present inaccuracies from the jittery motion of the eyes, such as you see there. It can present an offset or appear bigger and smaller than the actual target it's following. Because our technique identifies a target by its movement pattern and not its position, it also theoretically supports targets of any size and at any position, such as overlapping with one another. This is ideal for smartwatches as the screen space is very limited. Another advantage of dealing with relative movements is that our technique does not require calibration between the eye tracker and the display, as with gaze pointing. This is a tedious and lengthy process that you can see here. And that would be very hard to perform on a smartwatch, as the display is always in a different position when you look at it. But these are not the only advantages of using movement for input. Orbits leverages what is known as smooth pursuits, relatively slow and consistent eye movements that occur when your eyes follow a moving target. This is a characteristic behavior that facilitates the robust distinction from regular or more common eye movements, such as fixations on static points or saccades, which are the rapid movements in between these fixations. Furthermore, the human eye cannot generate smooth pursuits without external stimuli, making it hard for our technique to interpret input when none was intentionally provided. This is very important for wearable devices, as these may track the user's eyes constantly and thus be more prone to input mistakes. But how do we robustly distinguish between different targets moving at the same time? We do it by giving them different starting positions, by varying their angular speeds, and the third is to have some targets move in a clockwise manner and some others move in a counterclockwise manner. Another way to disambiguate between targets would have been to give them non-circular trajectories. We do not do this because a circle not only fits well with a shape of most watches, it matches the shapes on of the dials on the watch's face, and it's the smallest shape that would provide continuous smooth pursuits. We conducted 3 studies to validate orbits as a suitable interaction technique for smartwatches. The first was to find suitable algorithm parameters, the second to actually evaluate the performance of the technique, and the third was to test some different applications with users. So as I mentioned earlier, our technique works by performing a Pearson's correlation between the trajectory of multiple targets and the user's gaze. There are 2 major factors that come to play to enable this. The first is the window size. So how many eye and target data points do we need to collect before we try to correlate them? This basically translates to how long does the user need to look at a target to be able to acquire it. And while longer window sizes ensure the system performs more robustly, a window size too big and the system becomes unusable as the user needs to look too long at a target. The second factor that influences the performance of our technique is the correlation threshold. This is a value between 0 and 1 that indicates how sure the system needs to be that the user was looking at a target. A high value such as 0.9 might ensure that the technique makes little mistakes, but at the same time might ignore correct input, while a low value such as 0.1 might result in the technique incorrectly identifying target acquisitions. So in our first study to find these suitable algorithm parameters, we collected gaze data of participants performing 3 different tasks: following targets, reading the time on a watch while ignoring targets, and doing everyday activities. We first asked participants to follow different targets for 6 seconds at a time. These varied in their size and angular speeds. So the values in bold are basically just referring to that example. We then collected gaze data of participants checking the time while trying to avoid the same targets. And finally, we collected gaze data of participants doing everyday activities like reading a news article, watching a TED Talk, or playing a 2D video game. We selected these 3 tasks as they provide a wide range of different gaze input. After collecting this data, we plotted the following graph. So on the y-axis, we see the true positive rate. So often was the user trying to acquire a target, and the technique successfully identified that, and higher is better. On the x-axis, we see the false positive rate. So often did the user try to ignore the targets, or was doing any of the everyday activities, and the system incorrectly identified the target acquisition. So lower is better. And each colored line indicates the technique's performance under different window sizes. We locked the correlation threshold at 0.8 because from results from previous work on the topic. And we found that 30 samples provided us with a sweet spot that enabled users to acquire moving targets by following them for 1 second, because our system ran at 30 frames per second. So with these parameters, the bigger target with the medium angular speed performed best, with 96% correct activations and only 0.73% false activation when the eyes were not engaged with the system, so when they were reading or playing a video game. So having found these parameters, our second study focused on the orbit's performance on smartwatches. To accomplish this, we used off-the-shelf hardware such as the Pupil Pro head-mounted eye tracker and the Callisto 300. The big question of this study was how many targets can orbit support on the smartwatch interface. To find out, we explored the targets with the same sizes in the first study and with the two angular speeds that perform the best, and we introduce a new angular speed in between the two. With these, we tested 2, 4, 8, and 16 targets. And again, the values in bold is just refer to the example that we're using on the slide. The target in red was the one we told participants to follow. So we know the technique detected the correct target, basically. As before, we also asked participants to check the time on the watch while trying to avoid these targets. And again, we did this for all the conditions that we just described. Our results are promising. So on the y-axis, we have the performance rates of each set of targets displayed on the x-axis. And we do this for each angular speeds, aggregating the 3 different sizes together. So we see that the slowest speeds perform better, and that the system held its own until we added 16 targets. This is also true for when the user was trying to ignore the targets, which they found it really hard once we had 16 targets on screen. Encouraged by these results, we developed 3 example applications that help illustrate orbits in practice. We evaluated all these 3 after the second study and with the same participants and equipment. So the first was a music player. Let's see if I can operate this, which we use 3 orbits. The biggest one in the middle is the play. It has 1 target, which you'll see better once it starts moving. And then we have a volume orbit on the left and a skip orbit on the right. The volume and the skip have 2 targets each, moving clockwise and counterclockwise. So clockwise adds volume or skips ahead, and counterclockwise skips back or skips forward. And you can see that the user can play, he can raise the volume, and then he can skip to the next zone. And the red indicates when the user was actually interacting with a target. The second example was the notifications faceplate. Here we use 6 orbits, each with 1 target. These targets were color-coded to an app. So in red you have Gmail, in yellow you have Snapchat, and these indicated the unattended notifications on the phone. So the bigger the diameter, the more notifications these applications held. And this interface was done to highlight some of the unique qualities of Orbit's interfaces. This included how the selection area was no more than 0.1 centimeters, which would make it very hard to acquire with a finger. And these would actually expand when you were following any of these targets to give you more information. So once you actually need the information, it pops up and gives you a concrete number of notifications. So it saves a lot of space by only giving you information on a need-to-know basis. The last application was a contextual menu. The user is presented with an event, such as a missed call, and then once you acquire this target, he can then choose to call back, reply, store the number, or clear notification. And this was done to enable users to unconspicuously address common communication events that can occur in sensible or inappropriate situations, such as when you're in meetings or, so in summary, we have demonstrated the performance of orbits, arguably the first gaze-only input technique for smartwatches. We also addressed an early concern of ours that because movement easily attracts attention, that the users won't be able to consume information if targets are being displayed. And this is not the case, as they were able to check the time and only rarely activated any of the targets in doing so. Furthermore, our results are for an algorithm that performs in the worst-case scenario. We selected parameters that assume that the user would always be tracked, and it's easy to imagine this won't be the case. So it's easy to imagine that we would know when the user actually looks at the watch through some gesture or some other way. Also, our refresh rate of 30 Hertz is pretty low, forcing us to follow a target for 1 second to capture 30 data points. The current version of the People Pro eye tracker already supports 130 Hertz tracking, which would bring down the window size considerably and make the overall system much more responsive. Finally, we foresee various applications for orbits outside of the wearable domain, such as supporting interaction in smart homes using physical, light-based moving stimuli, We actually had a cool example last night in the NASCAR, so you could probably have some sort of interaction in the wild, or even using physical movement in the architecture. Thank you, and I hope for questions.
Thank you. That was very cool work. We have some time for some questions. All right, everybody's tired this morning, apparently. So I'm curious, would this work on head-mounted displays, like a Google Glass?
Sorry?
Would this work with something like Google Glass, a head-mounted display?
Yeah, so the technique doesn't require any particular hardware. So as long as the user can follow movement, so even if you can track the eye, you don't need a world camera, you don't need, you just need to know the position of the targets, which the Google Glass would know if he's displaying, and then you would need to track the eye of the user. So the current version doesn't do the eye tracking. I think you can blink, but they might be working on a new version that would do that. If someone knows, let me know.
Do you have a sense of how small you can make that, that angular movement of the eye?
So the small size we tested was 0.6 centimeters, which of course varies depending on how far you're seeing the target. But 0.6 still allowed us to perform at a distance of a wrist-worn device.
And I might have missed it. Did you control the distance between the watch and between the participant's head?
No, that wasn't one of the. So we offered. There was a picture where we offered some sort of stand because of fatigue, because our study lasted for more than 40 minutes. But it was a normal. We didn't vary the distance, which would be interesting to do.
Right. Did they move the watch closer so they could get a better view?
No, once we offered the standing, the stand, they would just rest the arm comfortably. So they could adjust it a bit more forward or backwards, but we didn't force a specific distance. It was something that they would felt comfortable with. And then once they were there, they normally would keep it there.
Oh, we've got a question.
So you mentioned that, sorry, my name is Diogo, I'm from Purdue University. Very nice talk, very interesting. I just wonder, you mentioned that you didn't force any distance, it was just what felt comfortable for the users. But did you guys did any study on that, like what distance, minimal or maximum distance you guys could measure with that system?
No, so that wasn't part of one of the questions that we tried to answer. So because we were in a very constrained space, so that's sort of a wristwatch, we used sort of the comfort zone. So we didn't try to push it how close we can get and how far we could. But that's a really interesting question that we definitely want to look into as we push the technique outside of wearables. That's definitely, it's one of the questions that we need to answer.
Because it could also be used for phones or tablets, right?
Yeah, exactly.
Or regular screens.
Yeah, but that's why we chose the smartwatch, because it's a very constrained environment that allows us to save.
Okay, thank you very much.